Roman numerals have two properties. The magnitude of the number, which denotes the size of the value or how far it's moved from 0 along the number line, and the direction that it's moved into, which is noted by a positive or a negative symbol in front of the number. By taking the absolute value of a number, we're only concerned with the magnitude of the value, not of its direction. And so this is why we remove the negative symbol from the value when we take the absolute value of it. Hence why an absolute value function returns only the positive values of the original number. This means that the two absolute value lines act like a set of brackets, requiring you to take the positive value of the numbers or values inside the absolute value lines first, and then complete any additional operations to obtain the final answer. So looking at the example shown here, the absolute value of 4 gives the same value as the absolute value of -4, simply because we're only concerned with the distance that the value has moved from 0 along the number line, which is 4 units, not the direction that it's travelled. In example 2, again, the absolute value function acts like a set of brackets, requiring us to take the positive version of 2, which is 2, and the positive version of -3, which is 3, and add them together to get our final result. Similarly, in example 3, we are required to take the absolute value or the positive versions of -6 and -3 first before completing any additional operations such as the square, and then subtracting both of those values from each other to obtain our final answer of -3. Now let's consider the graph of an absolute value function. Any absolute value function looks similar to its original function, but only includes the positive section of the graph. The most basic absolute value function is the graph shown here of y equals the absolute value of x. The graph holds similar properties to its original function, which is the line y equals x, which we know has a gradient of 1 and an x and y intercept of 0. However, once we take the absolute value of that function, y equals x, any negative values that were on that graph to begin with become negated. And hence this forces the graph to then mirror itself about the y-axis. Let's consider the value of the graph when x is equal to 2. The absolute value of 2 equals 2, and so substituting this value into the function y equals the absolute value of x gives us a y value of 2 as well. And we can see that that value exists here on our graph. And if we consider the y value when x is equal to -2, again we get the value of 2, since the absolute value of -2 is also +2. This will occur for all opposing values of x, and hence why the graph is reflecting itself. Similar properties also hold, just like with any other function that we have considered before. Changing the coefficient of x, or the value of a shown here, affects the gradient, and therefore will change the steepness of the line. By making it larger, the line gets steeper and therefore sits closer to the y-axis. By making it smaller, and hence a fraction, the line gets shallower and therefore moves closer to the x-axis. For example, the graph of y equals the absolute value of 2x moves 2 times faster than the original y equals the absolute value of x, and so therefore it will sit inside the original function as the y values are increasing twice as fast, and hence why we end up with a very similar looking function that sits closer to the y-axis. Adding a constant outside of the absolute value brackets will change the y-intercept, shifting the entire graph up or down to match the value of c. The graph y equals the absolute value of x plus 1, where the 1 is on the outside of the brackets, shifts the entire original function shown here so that the y-intercept, or the corner of the graph, moves from 0 up to y equals 1. The steepness is exactly the same as the original function, as the gradient hasn't changed, only that y-intercept. And finally, adding a value inside the absolute value brackets, such as the negative a shown here, will shift the function across the x-axis. Remember, to find the x-intercept, we set y equal to 0 and solve the equation to find the x value at that point. So, by adding a negative a inside the brackets, this shifts the entire function across to positive a on the x-axis. The gradient remains the same as the coefficient of x hasn't changed. However, the y-intercept does change because we have shifted the graph across, and you can find it by setting x equal to 0 and solving the equation. This means that for this case, the y-intercept has changed from 0 to positive a. Now let's consider some past Hsc questions. The most basic of the questions that they like to ask in the Hsc is simply just to sketch an absolute value function, as shown here from this 2006 question. It's generally considered an easier question. It occurred at question 1C of the Hsc in 2006. And if you notice, they've asked you simply to sketch the graph, and they have allocated 2 marks to it. So they are generally nice introductory marks that you can pick up easily. You have a couple of options here. If you understand how that plus 4 affects the original graph of y equals the absolute value of x, you're not required to show any of the algebraic working, such as finding x and y intercepts, in order to sketch the function. Remember though that in the marking criteria for this question, they will be looking for you to draw a graph that is easily readable, that has an appropriate evenly spaced scale, that you have used a ruler, and that your graph is about 1/3 of an A4 page in size. So, if we consider the function that we have here, they have added a plus 4 to the inside of the brackets. This means that we have shifted along the x-axis. So by considering the graph of the function y equals the absolute value of x, as shown here, and knowing that by adding that plus 4 inside the absolute value brackets means that we have shifted our new graph along to x equals -4, which we can also check by considering the algebra. For if we set y equal to 0 to find the x-intercept and solve the resulting equation, we end up with the absolute value of x plus 4 is equal to 0. As 0 is neither positive or negative, that gives us x plus 4 is 0, and so our x-intercept occurs at -4. So we can draw our shifted graph, which will maintain the same gradient as the original function, as both of them have a coefficient of 1 for x. And again, by checking the algebra, the new y-intercept for our shifted function gives us +4 when we substitute x equals 0. Again, the algebra isn't necessary for you to pick up the 2 marks, but it is a useful way for you to check that you have shifted the graph correctly. And hence we have the sketch of the absolute value of x plus 4. In this question from the 2011 Hsc, which occurred around the middle of the paper at question 4E, We've been given the sketch of two functions, one being the absolute value of x minus 2, and then the second being the concave down parabola y equals 4 minus x squared. The region between these two functions has been shaded, and we've been asked to write down the inequalities that describe the shaded region for 2 marks. Looking at the key verb here, write down or state, this question is just requiring us to identify the two correct inequalities that give us back that shaded region. Again, there are a number of ways that you can do this, the easiest of which is probably just to pick a value and check that it works for the region that has been identified. As the origin is included in the shaded region, it is the simplest of the values that we can check. And so we need to make sure that the inequalities we select work for the coordinate 0, 0. If we consider the absolute value function here, we can see that, again, we're starting with our basic absolute value function, y equals the absolute value of x, but this time, with the negative 2 being on the outside of that equation, it means that it has shifted the entire function down so that the corner sits at negative 2 on the y-axis. The region that they've shaded for this graph is appearing above that line, and so that leads you to the region being greater than the absolute value function. If we check the point 0, 0 for that inequality of y must be greater than or equal to the absolute value of x minus 2, remembering that because it's drawn with a solid line, it is also equal to, not just greater than. Substituting in those coordinates, that gives us that 0 must be greater than or equal to the absolute value of 0, which is just 0, subtract 2, giving us a true statement that 0 is a value greater than or equal to negative 2. And so hence the inequality holds because it works for a coordinate that exists inside our region. The second function, which is a concave down parabola that has been shifted to positive 4 on the y-axis, we can see that the region they have shaded appears below the parabola, hence leading us to the inequality that y must be less than or equal to, as it is a solid line, 4 minus x squared. Again, checking the coordinate 0, 0 that does exist inside that region, it gives us that 0 must be less than or equal to 4 minus 0 squared, which again is a true statement that 0 is a value less than or equal to 4. And so as both of these inequalities hold, the solution to our question is to write down that y must be greater than or equal to the absolute value function and less than or equal to the parabola.